In our previous lecture, we talked about using chemical equations to show the law of mass and the law of conservation of atoms. And we talked about balancing chemical equations, and we looked at doing some examples of that. Balancing equations in and of itself, of course, is not the purpose of balancing the equation, but rather to have a balanced equation to use so one can do what we call the quantitative part of a chemical reaction, or as we refer to it as stoichiometry. Stoichiometric calculations then are calculations based on a balanced chemical equation. So before we can do this quantitative stuff, we have to be able to balance then our chemical reaction. We started with reactants, we end up with products, and we have to have those balanced in terms of atoms. Now the quantitative part is very important to the chemist because what we want to do is to be able to use an equation and predict how much product should I be able to get if I combine 10 grams of this with 20 grams of that. I should be able to calculate it beforehand. If in fact mass is conserved in a chemical reaction and we have a balanced chemical equation, we should be able to make that sort of theoretical calculation. And that type of calculation is what we're talking about here then as stoichiometry. Now there's sort of a little roadmap that we can follow. We're going to look at basically 3 different types of problems, or I guess I could even say 4 different types of problems in this chapter, dealing with then starting with a known amount of something and asking for a known amount of an unknown in our overall problem. And we have sort of then a little roadmap here that we can follow as we go along. And each one of these arrows now is going to correspond to a mathematical conversion that we need to make. So in between each step here, as we go, for instance, from units of known to moles of known, that is going to involve then a conversion factor. So we're going to have a conversion factor that we're going to have between those 2 parts. That'll be one step. Then we're going to go from moles of known substance to moles of the unknown being what we're asking for. I mean, we obviously have to know what we're solving for. So it's the material identified in the question is how much of X, and then X becomes our unknown. We're going to have a conversion factor right here. And then if it says, instead of just how many moles of something, it might say how many grams of something, or later on we'll look in a chapter on gases and we'll talk about what volume of something, or in a chapter on solutions we may ask how many milliliters of a solution. But whatever the case is, then we may have a third step in here, so we will have a third conversion factor as we go from moles of X to grams of X to liters of X to whatever it is unit-wise that we want. Now this particular one right here is the one that is determined by, based upon the balanced chemical equation. So this is the step that we always have to turn to, having a balanced chemical equation to make that particular step of our solution. The first one is going to go back to some of the information that we know. For instance, if we start with grams and we want to go to moles of something, well, we've done that. We've made those conversion. If it's an element, we multiply by 1 mole over the number of grams, its atomic mass. If it's a compound, we use 1 mole over the number of grams of the formula unit. So we already have determined how we can go from units to moles. But this here is the part that's going to be determined now by our balanced equation. Now, as I said, we're going to really look at then 4 types of stoichiometric problems here today. We're going to look at what we call mole-to-mole problems. It doesn't focus real sharply. Mole-to-mass problem, mass-to-mole problem, and finally a mass-to-mass problem. Now, what that means is that in this particular case, our known is given in terms of moles, and the question asks how many moles of the unknown compound. In the second one, the first one would be given to us in the problem in moles, and it would ask us how many grams of something we are going to get. The third type of problem would give us the known substance in grams and ask for how many moles of something we're going to get. And the last one's going to give us a number of grams of something and ask for grams of something. So that's how we identify them. Not that there's any magical significance by those terms, but that's what we're given in some unit and we're asked for in some final unit, and that's the way we categorize then the stoichiometric problems. Now, if we relate these back to this roadmap, notice that if I started with moles of known, I would be right here. And I want an answer in moles of unknown, means I'm only going right there. And that tells me that in that type of problem, I'm only going to need one conversion factor. That's all I'm going. I'm just going one step on that roadmap because we're already part way there when we started, and we're only going to go part way to the end, and we only need then one conversion factor. If we look at the next one, we're going to start with moles, so we're right here, and it wants units in mass, so we see we're going to have to go from moles to moles, that's one conversion factor, and then convert from moles to grams, and so in that type of problem we are going to have 2 conversion factors in our problem setup. In the third type, we're starting with mass, means that we're starting over here. We have to convert it to moles of the known substance, but we want to go all the way to moles of unknown, so we're going to have to go to here. So we see that we're going to involve 2 conversion factors in that type of problem. And in the third one, we're starting here and we're going over here. So we're going to go 1, 2, 3. We have to have 3 conversion factors involved in our problem to go from the start to the finish. All right, now we're going to use unit analysis as we have in previous chapters. In other words, we're going to ask the question, how many moles, how many grams, how many something? And then we're going to say, what is it that we're starting with? We're going to be looking then for conversion factors. And those conversion factors may be the mass to mole ratio. It may be the mole to mole ratio from the balanced equation. But again, we're going to pay very close attention to the units as we set the problem up. When we end up with the same units on the right that we ask for on the left, we're comfortable that we have the problem set up correctly. So this is sort of just a quick guideline that when we look at a type of problem, we mentally then can click in and say, oh gosh, that should have at least 2 conversion factors in it. Or that one should only need 1 conversion factor. I still have to determine what the correct conversion factor is, but at least that gives me something to look at to say how many steps I need to go. Well, let's take a look at this chemical reaction right here. We have the reaction of C3H8, that is a hydrocarbon. As a matter of fact, it has the chemical formula of CnH2n plus 2. In other words, it's a saturated hydrocarbon. And what would that hydrocarbon's name be? This is one that we should remember. Anyone? Huh? No, not butane. Huh? propane. Okay, methane was the single carbon, ethane the 2 carbon, propane was the 3, and then butane was the 4 carbon. So this is propane. All right, so let's suppose that we have a propane grill, and we start it up, and we're operating it then, we're reacting it with the oxygen, we're burning the propane. This is the reaction that we're carrying out. Propane reacting with the oxygen in the air to give us carbon dioxide and water. Now, I'll just ask the question, and I think you can see this has nothing to do with the mathematic part, the stoichiometric part. This just has to do with the way that we read a chemical equation. If I want to react 1 mole of propane, how many moles of oxygen do I need? 5. That's what the equation tells us, right? That's the way we read that equation. 1 mole of propane reacts with 5 moles of oxygen to give us 3 moles of carbon dioxide and 4 moles of water. All right, so if I reacted 1 mole of propane, it would take 5 moles of oxygen. If I reacted 10 moles of propane, how many moles of oxygen would I need? 50. I must always maintain that 1 to 5 mole ratio. If I start with 1/10 of a mole of propane, I'll need 5/10 of a mole of oxygen. That's that conversion factor that will be in every problem we do. Every stoichiometric problem we do, we're going to have that one conversion factor, that one that takes us from moles to moles, which is this one right here, moles of known to moles of unknown. That's the conversion factor based on that chemical equation. That number ratio never changes. That is the balanced mole ratio for every species in there. One of these gives me 4 waters. If I get 4 waters, I had to have formed 3 moles of carbon dioxide. That's what the equation is telling us. All right, let's look then at our first example problem for stoichiometry. And this question says, how many moles of carbon dioxide would I be able to produce from the reaction of 2.85 moles of oxygen? The oxygen is reacting with the propane. So we have the propane there, but if we have only 2.85 moles of oxygen, how many moles of carbon dioxide am I going to form? Now, notice that this one, the unknown is asked for in moles. The known is given to us in moles. That's a mole-mole problem. And we're only going to need one conversion factor in this. And that conversion factor is going to be based on our chemical equation. So we write moles of carbon dioxide is equal to our measured quantity. This is our known, 2.85 moles of oxygen. And now we need a conversion factor. We need to convert from moles of the known substance to moles of the unknown, and that is dependent on our chemical equation. Well, going up here, we see the ratio between oxygen and carbon dioxide are 5 to 3 or 3 to 5, whichever way we need to use it in the problem. In this case, we want the moles of oxygen to be on the bottom, unit-wise to cancel. So we're going to have 5 moles of oxygen on the bottom, and we're going to have 3 moles of carbon dioxide on the top. Moles of oxygen now will cancel out, and we're going to be left then with the units of moles of carbon dioxide on both sides of the equation. Now all we would have to do, of course, would be our number crunching to determine the answer. Number of allowed significant figures, 3. These are exact numbers. That's not a measured quantity, that's a stated quantity based upon, of course, the law of conservation of atoms. So those numbers are exact. Okay? So the controlling part of the significant figures is this one, not this. So it's not 1, as it might appear, it's rather 3, the measured quantity. An example of a mole-to-mole problem. All right, let's go on and take a look at another one based on that same equation now. This time it's asking us how many grams of water can we get if we react 3.44 moles of oxygen, again with the propane. Well, this time then we're looking at the relationship of oxygen and water, but this time notice that we're asked for mass and starting with moles. That would be this type up here. That would be a mole to mass, and we're going to need 2 conversion factors in there. And I think these will become somewhat obvious as we set the problem up. All right, so let's go ahead. We're asked for grams of water, and we're starting with 3.44 moles of oxygen. Now, again, if we want to back up here and look at our roadmap for just a second, we're starting with moles of oxygen, so we're starting right here, moles of known, and we're going over here. So our roadmap tells us we need 2 conversion factors, and it not only tells us that, but it tells us that our first conversion factor is the one involving the balanced chemical equation. And that would probably make sense when we look at units, because somehow we have to get from moles of oxygen to moles of water. That's our first step in this case. So multiplied by 4 moles of water per 5 moles of oxygen. That's from our stoichiometric relationship in our balanced chemical equation between those two. Now we see that moles of oxygen have canceled, and we're left with moles of water. But we didn't ask for moles of water. We asked for what mass, how many grams. And of course we've done a lot of calculations of that type in the previous chapter. So now we want to multiply by a ratio of grams of water to moles of water. And so how much does 1 mole of water weigh? 18 grams. 2 for the hydrogens, 16 for the oxygen. So it's just like, all we're doing is calculating the formula mass. So we would calculate the formula mass for water, which would give us 18.02 grams using 2 places after the decimal. That cancels, and we now notice that we have grams for units on the right. We have grams asked for. Our units match. The problem is set up correctly. And so at this point then, it would only be a matter of plugging in our numeric values here to get an answer. All right? Again, as I mentioned in problem solving, it's not a bad idea to make a guessed answer first, just so that if you plug into the calculator and you see a number comes off drastically different than what you predicted, you probably need to go back and double check it. But just looking at this here, 4/5, that would be a little less than 1 times this would be about 3, and 3 times 18 would be about 54. So I'm just guessing that our answer should be something around 54 grams. Not 500, not 5, but 50. And so when I plug it into the calculator then, I at least have some general idea of what kind of number I should come out with. Well, let's see, what do we get here? We have 3.44 times 4 divided by 5 times 18.02, and our actual number turns out to be, with correct number of significant figures, 49.6 grams is our actual answer for the problem. But you see that 54 at least gave us the magnitude of whether it's in units of tens or hundreds or thousands or 10 to the minus 8 or whatever it might be. So it's a good idea just to kind of scan across and get a feel for what your answer should be. Well, this was an example now of our second type of problem there, which we call a mole to mass stoichiometric problem. Looking at another equation here, this time we have the reaction of a compound called chloroethylene. That's this one here. Remember in a previous chapter we talked about, well actually I'm incorrect on that. In this chapter we talked about the reaction of hydrocarbons with that group of chemicals called the halogens, fluorine, chlorine, and bromine and iodine. This is then a halogenated hydrocarbon. In other words, we've reacted a compound that had only carbon and hydrogen, and we have now replaced one of the hydrogens with a chlorine, which is one of the members of then the halogen family. Okay? And that, as I say, the name of this would be chloroethylene. That's a little different naming ending than what we were introduced to so far, but we'll talk about that type of name a little bit later in chapter 6 or 7. All right. As a matter of fact, this also has a common name of vinyl chloride, and it is used to make a chemical called polyvinyl chloride, which is one of our everyday plastic materials. Again, we'll look at that when we talk more about chemical bonding. But here we have then this halogenated hydrocarbon reacting with oxygen, and in the process we get carbon dioxide, water, and hydrochloric acid. And I'm going to pause a second. We have a question. Yes?
Do we have to worry about trying to balance those, or are they going to just be balanced in phase?
The question is, do we need to worry about balancing the equation? The answer is yes, you may need to balance the equation. And that's why, of course, we spent some time looking at how we go about balancing an equation. These calculations are dependent upon a properly balanced equation. Most of the ones in the problem sets, however, the balanced equation is already given. So unless it indicates that you must balance the equation, or it doesn't give you an equation at all, then of course you would have to write it and balance it. But for most of the problems you will find a balanced chemical equation. Okay? All right, let's see then what the question is this time. This time it says, how many moles of oxygen are needed to react 10 grams of the chloroethylene? Now this time notice that we're asking for the unknown in moles, and we're starting with the known in mass. And if we go back once again to our roadmap here, looking at, this time we're starting with mass over here, and we're asked for number of moles, so we're going here. And so we see that we would have two steps that we're involved with. We would need two conversion factors to make that calculation. And of course, one of those conversion factors, and I'll stress this over and over, but one of those conversion factors is going to involve the balanced chemical equation. That one is always in our stoichiometric problem. That's the one step that we always are going to be looking for. All right, so we start. We're looking for moles of oxygen, and we're starting with 10 grams of the compound C2H3Cl. The first conversion factor that we must make is to convert from grams of the known material to moles of the known material. And of course that's going to involve then the formula mass. So multiplied by 1 mole of C2H3Cl over whatever number of grams of C2H3Cl that we have. And of course we would then have to calculate that. So calculating it, we would have then of course 2 carbons, so that would be 2 times 12.01, 24.02, and we'd have 3 hydrogens, 3 times 1.01, 3.03, and 1 chlorine, 35.45, and giving us then a formula mass then of 0, 5, 7, 12, 6, 62.50. And now notice our units of grams have canceled. Okay? Now we have moles of the unknown substance. Moles of the known substance. Now we have to go to moles of the unknown. And for that we're going to turn to our balanced chemical equation. In this case we're relating now oxygen to the compound, and we see that 5 oxygens to 2 of those. And so now we'll put in another conversion factor here. We'll now multiply by 5 moles of oxygen per 2 moles of C2H3Cl. Now those units cancel, and we're finally left then with moles of oxygen, which was what we asked for. All right? Now again, we can get a rough idea of the answer because we see 2 into that's about 2.5. 2.5 times 10 would be 25, and 25 over 62.5 would be just a little bit more or a little bit less than a half. So we would expect our answer is something about maybe 0.35. So we'll go ahead and plug through on our calculator quickly then. We have 50. I'm taking the 10 times the 5, divided by 2, and then all of that divided by 62.5. And we end up with an answer of, actual answer of 0.400 moles of oxygen. And we can have 3 significant figures because we had 3 in the mass of the compound that we started with. Any question on any step of that one? The longest type are, of course, those that take us from mass to mass. And this is an example here. We're asked for how many grams of hydrogen chloride, so HCl, are we going to produce from 10 grams of C2H3Cl. So we have grams of this and we want grams of that. And in that case then we're going to, once again, following our roadmap, we're going to go from grams to moles, moles to moles of the unknown, and moles of unknown to grams. So we need 3 conversion factors in a mass to mass stoichiometric problem. So looking at this one then and setting it up, actually the first part of this is the same as we just did. Grams of HCl will be equal to 10.0 grams of C2H3Cl multiplied by. We just calculated the mass in the previous problem, so we already have that relationship set. Multiplied by 1 mole of the C2H3Cl over 62.50 grams. And I won't bother to write the whole formula down this time. Now we're at moles of the known substance. Now we're going to convert to moles of the unknown, which is the HCl. So now we need to multiply by the number of moles of HCl, which is 2, to 2 moles of the other one. So we have 2 moles of HCl per 2 moles of C2H3Cl. Now, you might say, well, isn't that kind of dumb to do that? 2 over 2 is obviously 1, and 1 times anything isn't going to change the number. Yes, that's true. It doesn't change the number, but the key thing is that we keep track of the units. And that is how we're going to change then from the units of our known to the units of our unknown. And so, yes, we do want to include it even though it has a number of 1. So, finally now, however, we don't want moles of HCl, we want grams of HCl. And so we will need to put in one more conversion factor, multiplied by the number of grams of HCl in 1 mole of HCl. And that again would be its molar mass, 1 hydrogen, 1.01, and 1 chlorine, 35.45, so 36.46 grams. And moles of HCl now cancel. Notice, again, we have grams asked for and we have grams determined. So we're comfortable we've set the problem up correctly as long as our units match, which they now do, and so therefore we would be ready to solve the problem. Well, eyeballing a quick check here, this would be about 30 over 60, which would be a half, and a half of 10 would be about 5, and so we know that our answer is approximately, excuse me, approximately 5 grams. So again, now we would plug in our actual numbers there. So we'd have 10 times that, so I can just put in 344.6 and divide that by 62.5, and we see that our actual final answer is 5.51 grams of HCl. Okay, question?
Should this last problem over here be 36.46?
Yes, it sort of looks that way. Good question. The question was, shouldn't this number be 36.46? And that is right. We just calculated down here 36.46. And so, yes, in fact, that should have been 36.6. Our answer would change slightly, probably 6.0. And I threw that in there as a mistake, and somebody was wide awake enough to catch that, you see. Okay, so you're paying attention. All right. Any other questions on the step process of this? All right. Well, let's just look at 2 more examples here. We're going to do many as we go through in not only this chapter and some other aspects in this chapter, but also future chapters. And it is important. It's important for your success in the course, actually, to have a good feeling for stoichiometric problems. We're going to do it here. We're going to do it in the next chapter after that, a chapter on gases later on. We're going to run into stoichiometric problems about half of the chapters we work with. So now is the time to get down exactly the steps that you want to use. All right, let's look at this problem here. This particular problem represents the reaction of oxygen with a chemical. Notice this is a hydrocarbon, but that particular hydrocarbon is acetylene. Okay, that's not one of the ones that we talked about as a saturated hydrocarbon, but it's a hydrocarbon, and that's acetylene, oxyacetylene torch. So we need 5 moles of oxygen to react with every 2 moles of acetylene. And in the process, we see we produce 4 moles of carbon dioxide and 2 moles of water, and of course heat energy. And we're going to look at energy's contribution in stoichiometry here just a little bit later in the chapter. Now, the question this time is, how many moles of oxygen do we need to react 86.4 grams of the acetylene? Notice that our known is given to us in mass, and our unknown is asked for in moles. This is a mass to mole type problem. So just mentally starting to think of the steps before we ever write anything down. I'm going to think I need to change from grams of this known substance to moles. Step number 1. And then I need to change from moles of this to moles of the unknown, step number 2. And in that case, that's as far as I need to go. So I need 2 steps in the problem. So moles of oxygen are equal to 86.4 grams of C2H2. And the first thing we need to do is change from grams to moles. So multiplied by 1 mole of acetylene per the number of grams, which would be 26.04 grams. That's the molar mass. So I just calculated that quickly in my head there so that we could use it. Now we have the moles of the acetylene. Now we need to use our stoichiometric relationship to get to the next step. And we see that from our equation. Up here we have a 5:2 mole ratio. And we use it in whatever fashion we need to cancel the units out. In this case, we want the 5 moles of oxygen on top, and we want the 2 moles of acetylene, HC2H2, on the bottom. Our units cancel, and notice at this point we have moles of oxygen on both sides of the expression, unit-wise, and we're comfortable we have the problem set up correctly. Again, running through a quick calculation here, we would have about, this is 2.5 times 100, it'd be 250 divided by 25, so our answer is going to be probably something a little less than 10, we'll say about 9 moles, and we'll go ahead and plug in and see what we actually get. 86.4 divided by 26.04 and multiplied by 2.5, and we get an answer of 8.29 moles of oxygen. Okay? All right. Now, the last one of this type that we'll do then is grams of carbon dioxide produced, along with 6.85 grams of water. So in this particular one, we're saying if in the reaction I got 6.85 grams of water produced, how many grams of the carbon dioxide would I have also produced? Now our ratio doesn't have to be reactant to reactant. It doesn't have to be reactant to product. It can be product to product or product to reactant or reactant to reactant. It can be any relationship. As long as we have the balanced equation, we can relate this to that or this to this or this to that. It doesn't make any difference. All right? In this case, then, we're asking for how many grams of carbon dioxide would I have produced if I had produced 4.85 grams of water. Now notice this time we're starting with mass. We're asking for mass. So thinking of our roadmap, we're going to go from mass to moles, one conversion step, moles to moles using our balanced equation 2, and moles to mass, then 3 conversion factors in our roadmap. And so now we're ready to set up the problem, keeping in mind we need 3 steps in there. So grams of CO2 are equal to 6.85 grams of water. And the first step then will be to change that to moles. So we're going to multiply by 1 mole of water over 18.02 grams of water. We calculated that just a moment ago, so we've done the first step. We now need to use our balanced equation to relate then the moles of the CO2 to the moles of water. And we look up at our balanced equation, 2 to 4. And so we see that we have 4 moles of carbon dioxide for each 2 moles of water that were formed. And we now notice that our waters cancel out. And finally then, we now need to change from moles of carbon dioxide to grams of carbon dioxide. Whoops, not an equal sign, a times. And how many grams of CO2 are there in 1 mole of CO2? Well, we would have to add it up, 12 for the carbon and 2 times 16, 32 for the oxygens. We would have 44.01 grams of carbon dioxide per 1 mole. Again, we note now that we have grams of carbon dioxide on the right. We ask for grams of carbon dioxide. Our problem should be set up correctly. And a quick span across, we have 6 over 18. It'd be about 1/3 times 2 would be 2/3, and 2/3 of this would be about 30. And so our answer should be approximately 30 grams when we make our calculation. Again, we'll calculate it quickly. 6.85 divided by 18.02 multiplied by 2 and multiplied by 44.01, and we get an answer of 33.5 grams of carbon dioxide for our answer. Any question on that particular type of calculation? Now, all of these problems we've calculated are based on the concept that when we put reactants together, that they totally react to form products. In other words, what we have calculated in each case is a theoretical value. Theoretically, this is what we should get, provided that everything in the reaction actually does undergo a chemical change. In many reactions in nature, this doesn't occur. We only get part of the reactants that really become products. And so what we're going to look at in the next part of stoichiometry is what we refer to as percent yield. In other words, how much of our product do we really get in the chemical reaction? Percent yield is defined as the grams that we actually get divided by the grams theoretical multiplied times 10 to the second to put it into percent. This right here, I'll put a little asterisk here, that is what we get. That's the number that we obtain when we do a stoichiometric problem. When we do a stoichiometric problem, we're calculating the theoretical value. In other words, in that last problem where we had the 33 grams of carbon dioxide, that is based on theoretical that 100% of the compound reacted. All right? Let's look at an example here in the book. And this example gives us a reaction of Fe2O3 reacting with carbon to produce iron and carbon monoxide. And the question is, what is the percent yield if a 438 gram sample of this produced 275 grams of this? So this is what we actually obtained. The question is, what should we theoretically obtain? And if so, once we calculated the theoretical, we can, of course, calculate the percent yield. Now, this is a mass-to-mass problem, which most percent problems are going to be given as. And so we're needing to go from grams of this to grams of that in our calculation. So we would ask the question, how many grams of iron would we get from 438 grams of Fe2O3? We would have to change from grams to moles. So 1 mole of the compound per number of grams of the compound. And we would look up there for iron, 55.85. And we have 2 of those. And we have 3 times 16 or 48 for the oxygens. And so we have a mass of 0, 7, 9, 10, 159.70. That takes care of the grams of that. Multiplied by, okay, now we're at moles. Now we need to go moles of unknown. 2 moles of iron per 1 mole of Fe2O3, and so that unit cancels. And then we need to convert from moles of iron to grams of iron, multiplied by 55.85 grams of iron per 1 mole of iron. And so that unit cancels. Now this is grams of iron theoretical that we're calculating. Well, let's see. I'll plug that in real quick here because we need that number to do our final step. So we have 438 divided by 159.7 multiplied by 2 and multiplied by 55.85. Theoretically, if all of this reacted, we should be able to produce 306 grams of iron. Now, we see that we didn't produce that amount. The actual reaction gave us only 275 grams, and so therefore, now we can calculate what percent yield, what percent of the theoretical amount did we actually obtain. So percent yield is equal to 275 grams divided by 306 grams times 10 to the second. Of course, our grams cancel. Percent is a unitless number. And we have a percent yield of 89.8% yield. All right. In our next lecture, we will come back and explore percent yield a little bit further. We'll also go on and talk about one more aspect of stoichiometry, referred to as the limiting reactant part of stoichiometry, and we'll take that up then in our next lecture.